This is CGTN, China Global Television Network.
I'm Shini Somara, finding out about drone photogrammetry and how it can help us understand the migration patterns of grey whales.
And I'm in Iceland, where an innovative energy company is turning CO2 into stone.
In the spring of 2019, an unusually high number of grey whales were washed up on the eastern Pacific coast of Mexico, the USA and Canada, either dead or dying. They didn't show any signs of having been caught in fishing nets, nor have biologists found any signs of a toxic spill or outbreak of disease that would account for their deaths. They had simply left their breeding grounds in Mexico and never made it back to their feeding grounds in the Arctic.
This was declared an unusual mortality event by NOAA Fisheries in the US, which is an event where a lot of animals are dying and critical or urgent action needs to be taken to figure out what's happening.
So why were the whales dying? Assistant Professor Fredrick Christianson and his team had secured funding in 2017 to study these whales, particularly their migratory patterns, so they were in a unique position to help solve this mystery.
We don't know that much about whales and like what's called bioenergetics. So it's basically like how much energy do they require to function, how much energy does it cost them to grow, how much does it cost to reproduce and to survive and so on. The only way to get this information historically is from whaling records. So we had to kill the whales and measure them and measure how much oil they have, how thick their blubber is and so on.
Professor Christianson has been using drone technology to measure the bioenergetics of whales in a non-invasive way. So how do the drones work?
We just fly this over the whales at maybe 20-30 meters altitude. It has a camera on board that we face directly down in a perfect 90-degree angle. And if the drone is moving because of wind, there's a gimbal that keeps this camera completely steady. So you always get a perfect picture from above. So we can measure from the photographs the number of pixels, that's the length of the whale, and the width of the whale. We do this when the whale comes up to the surface to breathe, so you can actually clearly see the whole contour of the animal. And by knowing the altitude and knowing the camera focal length, the picture resolution and so on, we can actually convert these pixel measurements to actual meters. So we can measure how long the whale is and how wide it is. And from that we can calculate its volume. And by looking at the volume relative to how long the animal is, we get a metric, so kind of an index of how fat the animal is, so its body condition.
Grey whales were once called devilfish on account of how ferociously they protected their calves from whalers who hunted them to the brink of extinction. Their population has now bounced back, and they play a crucial role in regulating our climate. Their dung fertilises the phyto, or plant plankton, which is a key carbon sequester. Like the blue whale, humpback and right whales, they have baleen, a filter feeding system similar to bristles inside their mouths instead of teeth. They use their baleen to collect shrimp-like krill, plankton and small fish found in the cooler northern waters.
Most of these species spend half the year feeding in one location, normally close to the polar regions. And then they use all this energy, they build up these fat reserves that they then carry with them on their bodies, in their bodies, to the breeding grounds during the winter. And during that time, they're not feeding at all. So for them, having really a lot of fat is essential for their reproduction and their survival. So to understand how body condition, how you can measure it and how you can relate it to survival and reproduction is fundamental to understand anything about the ecology of this species.
The drones allowed for many more whales to be easily monitored from the air than with traditional boat-based techniques.
And we can identify the animals from the color patterns on their backs, both from the drone, or if operating from a boat, we can also take pictures of the flank and identify them. So by doing that, we can actually monitor the same individual for as long as they stay in Mexico, basically. We can photograph the same animal over time and measure how its condition changes. We can see how mothers, for example, are getting thinner, whereas their calves are growing in size and so on.
But over the 4 years of monitoring, something shocking was revealed.
We can see a trend in how the population condition changes over the time. All the animals are declining in condition, which would be expected because they're not feeding. But they're declining to a level which is really low before they start heading north. And that level is much lower in 2018 and 19 compared to 2017, which makes me believe that the animals are losing so much condition that they're getting very close to their starvation threshold. And some animals are gonna have passed that threshold and end up dying before they get back to their feeding grounds where they can replenish their energy reserves.
So where along their migration routes are they perishing and why?
It's on the return journey. So if it's caused by starvation, which our data suggests it is, that would kick in most severely at the end of the season because that will have been the longest period of time that they haven't been feeding.
And do you know what's causing this?
Because we're seeing this decline is happening even when the whales are arriving in Mexico, something is most likely happening in their feeding grounds. So continued research up there to look at the condition of those animals is the most important, I think. And trying to correlate that with climatic effects and prey availability.
Saving these beautiful creatures is part of a much bigger picture of supporting animal populations during unprecedented climate change.
Understanding how the Arctic ecosystem is affected by climate change and how this is affecting the prey of the gray whale will be very valuable in itself. From that, we can start making predictions of seeing, given different future scenarios, how can we expect the population of gray whales to respond to this? And I think that will then be very important to regulate other things. I mean, we should try to stop climate change, that's for sure, but that's a major challenge. There's also other threats that face this population. And I think if we can see that climate change is already going to make this population much more vulnerable, it's important to start addressing these other threats in context of that, to say, okay, now we don't have 26,000 gray whales anymore, we're dealing with, let's say, 15 or 20,000. We have to increase the protection of these species to make sure that other threats are not causing cumulative impacts that can affect this population.
You can see more of Razor on our YouTube channel. Search for Razor Science Show and it will take you straight there. Remember to subscribe and hit the bell button for notifications.
Life moves pretty fast. Ideas move at the speed of sound. Technology moves at the speed of light. If you don't filter out the noise, you might miss the details. We pay attention to the details because they matter, showing you a different perspective. See the difference.
When you think about space, you probably imagine a vast, pristine void. You think space. But the area closest to Earth, known as low Earth orbit, is actually littered with junk, defunct satellites, discarded rocket stages, and debris from collisions and explosions. There are estimated to be nearly 1 million items of orbital debris larger than 1 centimeter, reaching up to 15 kilometers per second, 10 times faster than a bullet. Even the smallest of these could penetrate the shields of the International Space Station's crew modules. More than 28,000 objects larger than 10 centimeters are tracked from Earth. At this size, they could shatter a spacecraft. The amount of space junk is rising rapidly. The ISS had to reposition 3 times in 2020 to avoid collisions with debris. If this trend continues, it could trigger the Kessler syndrome, a catastrophic chain reaction of collisions rendering some orbits unusable. As the zone is occupied by crewed space stations, missions en route to deeper space, and most of the satellites that provide cell phone reception, internet, GPS, weather forecasting, and more, the impact would be vast. So what can be done? Special spacecraft fitted with nets, harpoons, robotic arms, or lasers might offer a solution for deorbiting larger items, but these missions are likely to be complex, expensive, and risky. In the long term, it would make sense to reduce the amount of junk that gets there in the first place. Ideas include a tax on launches and charging fees for the duration of a satellite's time in orbit. Eventually, all spacecraft should be able to deorbit themselves if we are to avoid our nearest region of space becoming a no-go zone for future generations.
With lockdown easing and summer fast approaching, international flights are starting to pick up. The vaccines protect us against severe disease, but not necessarily transmission. And there are so many different COVID-19 variants out there. Is it really safe to travel? Let's revisit a piece that I made during the first lockdown over a year ago, where we looked at measures airlines are taking to reduce infection.
A study of a commercial flight in 1979 helps us understand how viruses can spread in confined spaces like planes. 54 passengers were on board and delayed for 3 hours before takeoff. At this time, the ventilation systems were not functioning. 72 hours after the flight, 72% of the aircraft passengers became infected with influenza, all from one infected passenger who had boarded the flight. Ventilation systems on most commercial airlines are specifically designed to circulate air. Air in the cabin is refreshed every 4 minutes through HEPA, or high-efficiency particulate air filters. Cabin air is blasted through a 3D mesh of microglass fibers to capture microscopic particles and deadly germs. The SARS-CoV-2 virus is microscopic, measuring approximately 125 nanometers in diameter, which is similar to other viruses like influenza. It's smaller than bacteria, which range widely in size, but start from around 1,000 nanometers and a fraction of the size of a red blood cell, or the diameter of a human hair. The gaps in the HEPA filter are large enough for a virus particle to pass through, but they're still caught by Brownian motion. Smaller gas particles are shot through the filter. These knock the virus particles around in a zigzag-like fashion, increasing the probability of collision with one of the mesh fibers, where it's then deposited. HEPA filters on board modern aircraft remove 99.995% of all virus particles, and the air is recycled through the cabin 20 to 30 times every hour. Regular maintenance and replacement of the filters is required to maintain that level of efficiency. However, even though the filters are nearly 100% efficient, within those 4 minutes, air has usually mixed across 3 to 4 rows in front and behind. Professor Chin-Yan Chen and his team have modelled different scenarios within air cabins to study how particles can circulate.
So you can see that the cough or talk, the droplet is go up to the ceiling level, then the ventilation system brings it down along the walls of the window and to the floor level, and then it could really go to the other side of the aisle, and then finally form this mixing condition.
Another well-studied flight on March 15, 2003, a Boeing 737 carrying 120 people flew for 3 hours to Beijing from Hong Kong, where a 72-year-old man with Sars had boarded the plane. The World Health Organization could only make contact with 65 people 8 days after the flight, but of those, 22 were found to have been infected with Sars. The majority of those were located close to the 72-year-old man, indicating localized infection. However, infected passengers were identified throughout the cabin, and it's believed they had no contact with the infected person, either before or after the flight. This has perplexed epidemiologists.
So in these journeys, this person infected more than 20 fellow passengers in the airplane, and then 4 of them died as a result. Which means the seat next to this sick passenger is a very high-risk seat. But you also see from this seat map, passengers sit as far as 7 seats could get infected. So we also suspect that the wake caused by a walking passenger or a walking flight attendant could bring these particles very far.
The challenge facing scientists in the aviation industry is understanding exactly how SARS-CoV-2 is transmitted from an infected person to another person, which is more complicated than you might think. We know that SARS-CoV-2 is primarily excreted through respiratory droplets which leave the mouth and nose. Professor Qingyang Chen and his team have designed a new ventilation system that doesn't mix the clean air in the cabin. Rather than from above, it's supplied from below, directly to your breathing zone. Then when you breathe out, the contaminated air rises and is extracted at ceiling level.
So as a result, you are not sharing the air with your neighboring passenger. With our new design, we anticipate that we could reduce the risk of infection by about 50%. It's something I hope that the airplane manufacturers are willing to implement.
So when we're back on planes, how will things be different?
As you can see, most of US major airliners are asking passengers to put masks on. And some of them also leave the middle seats open. And I think this is a very important first step for the airliners to take those measures to mitigate the risk. I have to say that nothing is bulletproof. When you travel, you always have a risk. And risk is not only occurs in the air cabin. It could occur in the terminals, could occur in the buses or the subways. We hope that the airliners will take proper measures as I have described here. And this will be very important for building the confidence on the passengers.
For more science, behind-the-scenes insights, groundbreaking research, and even some fun, check out our Razor podcast. Search Razor Sounds on all major streaming platforms, and remember to subscribe so you don't miss out on any episodes.
How will your world change today? What happens here? What happens there? Or what you make happen for yourself? If it matters to you, it matters to us too. Your stories are the stories that need to be told. Africa Live. Find your voice.
On the agenda with me, Stephen Cole, we look up into space. We look down into data. We look at debt. We look at politics. We look at opioids, climate change. We look at all the issues that really matter around the world. But you matter too. We want to tell the stories you want to see and hear about. Make it your agenda.
The world economy as we know it is about to change. Global business reports highlight emerging markets, developing countries, and dynamic sectors worldwide. We feature top analysts and newsmakers to provide perspectives on every facet of business. From an on-the-ground perspective, we provide you with balanced and objective assessments. Fast, sharp, and insightful. Global Business, only on CGTN.
According to NASA, the levels of carbon dioxide in the atmosphere are higher than they've been at any time in the past 400,000 years. Scientists think one way of reducing levels is right under our noses. I'm Emma Keeling in Iceland, where they're taking carbon dioxide from the atmosphere and turning it into stone. Iceland is one of the most geothermically active countries in the world. All of its electricity comes from this renewable resource. The Hellisheiði power plant just outside of Reykjavik is one of the biggest in Europe. Steam is accessed from underground to create the power, but it brings CO2 with it. Dr. Edda Adadottis from Reykjavik Energy is the project manager of a joint venture called Carbfix, pioneering a process to capture that CO2.
So we think of geothermal as, all very natural, but actually it is emitting CO2, isn't it?
This power plant, for example, only emits 3% of the CO2 coal-burning power plant of the same size emits. Last year, we captured and injected a third of the CO2 emissions from the power plant.
So how do they capture CO2? Steam and hot water are pumped to the surface. To generate electricity, the steam drives the turbines and is then cooled and condensed. Gases like carbon dioxide and hydrogen sulfide from underground are pumped out of the turbine into the scrubber and showered with pure water. Here, CO2 and other gases are dissolved and the non-water soluble gases are vented.
Just like that?
Just like that.
It seems very simple.
It is very simple.
It's almost too simple.
Well, very often the best solutions are the most simple ones, so yeah.
The CO2 mixture is then piped over to the injection site.
And are all these igloo-looking things, are they all the injection sites, are they?
Yeah, each one of those is an injection well.
Yeah. A well, okay.
A well.
So this is the whole site, but these are all wells?
Yeah, exactly.
Okay. Why igloos?
It's to protect the equipment inside from the harsh weather during winter.
And it looks good?
It looks good, yeah. This well is about 2 kilometers deep.
Wow.
It's closed off down to 700 meters, meaning that what we inject can only exit the well, go into the bedrock below that depth. And then reactions that occur in nature between the rock and the dissolved gases turn the gases into stone.
Nature plays a big part. Basalt rock is cooled lava and contains calcium, magnesium and iron, which reacts to the CO2 mixture, forming solid calcium carbonate in the rock's pores.
So this is a core we drilled into the storage formation a few years back. And then we have the white veins and spots in between, and that's mineralized CO2. And turns out that what we inject is turned into rock like this in less than 2 years. So it's a very efficient and effective process, permanently getting rid of CO2.
Iceland is now looking at applying this technology to heavy industrial plants and other CO2 emitting sources in the country. Wherever there is basalt rock, this process can work. It's the most common rock type on Earth, covering around 10% of continents, while most areas within the Earth's ocean basins are underlain by basalt.
The storage capacity is huge.
Professor Sigurd Larsson is the co-founder of Carbfix.
On a big scale, we looked at all of the oceanic ridges. Of course, it's probably not economical to do it, but you could take all the CO2 from burning of all fossil fuel that we know of on Earth. You could take that CO2 and you can store it into all of the oceanic ridges. There is enough storage capacity for it, but we will not do it. It's not economical to do it. You will find the solution closest to the source. For example, if you're burning here, you have a coal-fired power plant here in Northern Europe, it might be best just to put it in the sedimentary basins here close to Norway, a short distance for travel.
One disadvantage is the amount of water needed for the process. It takes around 25 tonnes to convert 1 tonne of CO2.
I mean, we don't have enough water, do we?
Exactly, and that's why we are, when we take this and expand this all over the world, this method, we're going to need something else. Therefore, we're going out to sea. There's infinite source of water on the coastline. But what's tricky with seawater contains dissolved sulfur and calcium to start with. And at high temperature, if you go much higher than 150, this sulfur can steal the calcium away from the calcite that we want to form. So we are trying to define the temperature window, where we can inject, and that means temperature window is actually how deep down in the earth can we put our injection wells, because it gets hotter and hotter as you go down. So these experiments will help us to define how we can play with seawater when we inject. This is, as we say, very hot stuff. and it looks like, it's working very well.
You're very busy.
Well, yeah, we are all very busy, and we should all be very busy when we're trying to save the world. What we're doing is just a drop in the bucket. Presently, we are emitting about 40 gigatons per year of CO2. We have to be extremely focused to get going, to capture CO2 as fast as we can. And then later on, in the second half of the century, we have to clean it from air, because we're not doing it fast enough.
Carbfix is also collaborating with Swiss company Climeworks to capture CO2 directly from the air. The prototype unit at Hetlethady captures around 50 tonnes a year.
Even here in Iceland, we might build power plants just to drive air cleaning systems. And that might be a great role where Carbfix could play in the future, simply cleaning the air for the better of mankind.
So a fly doesn't try to kind of slow down very much and then land like a bird. It's using a very different mechanisms. It basically flies, it does slow down, but it can also crash land into the surface and use its mechanical structures to dampen this impact. So this we call mechanical intelligence or physical artificial intelligence, which is a very important method in nature of how to make animals robust to move in unknown outdoor environments.